Welcome, my dear students. Today we are going to see two topics, topic 12.6 and 12.7 of chapter 12, that is thermodynamics. So, first of all, let us see topic 12.6, that is about specific heat capacity. First of all, we have to understand what is heat capacity. See the definition. The amount of heat required to increase the temperature by 1 unit of a given mass is known as heat capacity of the substance. Suppose you have taken some substance and you want to increase the temperature by 1 unit. So obviously you will require some heat. So that heat which increases the temperature by 1 unit of any substance is known as heat capacity. That is denoted by capital S, and obviously capital S will be equal to delta Q upon delta T, where delta T is the change in temperature and delta Q is the heat supplied. Obviously from this you can say the unit will be joule per Kelvin, right? Now let us see another definition, that is specific heat capacity. This was heat capacity and here it is specific heat capacity. The amount of heat required to increase the temperature by 1 unit of a unit mass of substance is known as specific heat capacity. You have to note one thing, dears, that here in the first definition there was a word given mass, but in the second definition you can see it is about a unit mass. So the energy required to increase the temperature by 1 unit of a 1 unit mass is known as specific heat capacity of the substance, and that is denoted by small s. This was capital S and here it is small s. So obviously small s will become delta Q upon m delta T, right? Here it is about unit mass, so obviously m will be in denominator. So this is specific heat capacity, and here delta Q upon delta T is capital S already, that means heat capacity, and so it is capital S upon M. So specific heat capacity is heat capacity per unit mass, that also we can say. I repeat, specific heat capacity is heat capacity per unit mass. Alright, and from this equation itself you can derive the unit of specific heat capacity. Here delta Q is heat, so that's why the unit will be joule. Here this is mass, so unit will be kilogram, and delta T is temperature, so unit will be Kelvin. So unit becomes joule per kilogram per Kelvin. Now let us see molar specific heat capacity. Mind well that here it was unit mass and now we are going to see unit mole. Let me show that. Molar specific heat capacity. The amount of heat required to increase the temperature by 1 unit of 1 mole substance is known as molar specific heat capacity. Again note that here it is 1 mole. It is about 1 mole. So let me explain again. The amount of heat required to increase the temperature by 1 degree Celsius of a 1 mole of substance is known as molar specific heat capacity. Note that if you put here 1 kg, then it becomes only specific heat capacity, but when you put 1 mole, then it becomes molar specific heat capacity. Students, this is mostly used for gases, though it can be used for solid and liquids also, but it is mostly used for gases, because in gases what's the case is that you cannot measure the mass of a gas. Suppose we are talking about the gas in this room, alright, the room in which you are sitting. So the mass of that gas is very hard to calculate, but the amount of mole of that gas can be calculated easily, and that's why for gases molar specific heat capacity is widely used. Now the molar specific heat capacity is denoted by capital C, and that will be capital C is equal to delta Q upon mu delta T. You know that in specific heat capacity the equation was delta Q upon m delta T. Here it will be mu delta T, where mu is mole number. Also, this delta Q upon delta T is capital S, heat capacity capital S. So we can say that molar specific heat capacity is basically heat capacity per unit mole, right? Now let us see the unit. For delta Q, obviously you can write joule. For mu, you can write mole. And for delta T, you can write Kelvin. So it becomes joule per mole per Kelvin. That is the unit of molar specific heat capacity. Here you should note one thing, that both S and C, S is specific heat capacity and C is molar specific heat capacity. They both depend on the nature of substance and the temperature of substance. Remember, nature of substance and temperature of substance. Now also note this additional equations that I already derived from the previous equations. Delta Q is equal to ms delta T, and another equation is delta Q is equal to mu C delta T. See, if you have been asked that find out the heat required to increase the temperature by delta T of any substance, then you can use these equations. Now, if you have been given mass of the substance and specific heat capacity of the substance, then obviously you can use this equation, delta Q is equal to ms delta T. But if you have been given mole number of the substance and the molar specific heat capacity of the substance, then obviously you have to use this equation, delta Q is equal to mu C delta T. Now let us see this information. Molar specific heat capacity of solids at room temperature and atmospheric pressure is almost constant except carbon. See, for solids, the molar specific heat capacity at room temperature and atmospheric pressure, that means 1 atmosphere pressure, remains constant, and that we can see from this table. See, here all the substance are given. These are all the solid substance you can see, and these are the specific heat capacity of this substance, as well as here these are the molar specific heat capacity of the substance. You can see all of these molar specific heat capacities are almost same except for carbon. See, the values are like 24.4, 24.5, 26.5, 25.5, 24.9 and so on. And even more surprising thing is that all of these values are nearly equal to 3R, where R is universal gas constant. You know the value 8.314, right? So if you multiply 8.314 with 3, then you will get almost these values. As I said, here carbon is one exception. You have to just ignore it. Otherwise, for all other solids, the molar specific heat capacity at room temperature and room atmospheric pressure remains constant. Now, why it is so, that we are going to see here. See the reason. For a solid atom, average energy for one dimensional motion at T temperature is given by kBT. Here kB is Boltzmann constant and obviously T is the absolute temperature of the substance. Now, first of all, let me tell you that this equation will be coming in detail in chapter 13. The explanation about this equation is basically given in chapter 13. So here we'll just accept this equation. What is this equation about? That if you take any atom and if you consider the one dimensional motion of that atom at T temperature, then the energy associated with that atom will be kBT, right? See, every atom is having some sort of motion due to thermal energy. Other than absolute zero temperature, means 0 Kelvin temperature, every atom is having some sort of motion. So, if the temperature is, let us say T, then the energy associated with one atom in one dimension motion will be equal to kBT. So, obviously if we take 3-dimensional motion, then it will be 3 kBT. So, for the 3-dimensional motion, the energy will be 3 kBT. Thus, the average energy for 1 mole of atom will be obviously U is equal to Na into 3 kBT. See, we are talking about 1 mole atoms. That means it will be equal to Avogadro number Na. So, Na multiplied by 3 kBT, that will be the total energy of 1 mole atoms. Now, when we talk about total energy of atoms, so it is nothing but the internal energy of the substance, right? And that's why here we are using the symbol of internal energy U. So, U is equal to Na into 3 kBT. But Na into kB is also R. Na is Avogadro number and kB is Boltzmann constant. So, multiple of them becomes R. So, we can write U is equal to now 3RT. And that's why delta U can be written as 3R delta T, where R is constant, you know already. Now, at atmospheric pressure, the pressure remains 1 atmosphere constant. And we know that at constant pressure, the heat required is delta Q is equal to delta U plus P delta V. This is nothing but the thermodynamics first law at constant pressure. Now, when we are talking about solids, so in solids, by changing the temperature and so on, the volume will not change much. That means delta V will be almost equal to 0. Now, if delta V is 0, then this term becomes 0 and so delta Q will become delta U. Now, come to the molar specific heat capacity of solid, which is basically given by C, and C is equal to delta Q upon mu delta T. But here from the very beginning we are talking about 1 mole. See this here, 1 mole. And that's why we can write mu is equal to 1. So here mu is equal to 1, and that's why the equation becomes C is equal to delta Q upon delta T. But delta Q is delta U, so it is delta U by delta T. But again, here we have seen that delta U is 3R delta T. So I can place here 3R delta T upon delta T. So delta T will be cancelled out and we will be getting 3R only. So C becomes 3R. Mind well, this C is molar specific heat capacity and we are talking about solid right now. So for solids, the molar specific heat capacity is 3R and R is constant. That's why 3R is also constant, and that's why only in the previous table we have seen that molar specific heat capacity of all the substance except carbon were coming constant, and that was all equal to 3R, right? Now let us see specific heat capacity of water. Why we are discussing about specific heat capacity of water spatially? There is one reason. See, specific heat of water slightly varies with temperature. See this graph here. On this axis there is specific heat and here is temperature. So you can see that initially the specific heat is higher, then after it decreases and then again it increases with respect to the temperature. Though the variation is very small, you can see this is 1.008 and this is just 1.000. That's all. So the difference here is something like 0.008 only. Alright. So the variation is very less, but yes, there is some variation. Now, why this variation matters? The answer is that when we define calorie, you know the previous definition of calorie, it was like the amount of heat required to increase the temperature of 1 gram water to 1 degree Celsius is known as calorie, right? But here there is a problem, because the specific heat of water is not constant. So obviously at different temperature, the definition of calorie will give you different values of calorie, and that is obviously not good, right? So for the precise definition of calorie, we have to take certain temperature difference at some particular temperature, and that is done in this new definition. Look here, So precise definition of calorie is 1 calorie is defined to be the amount of heat required to raise the temperature of 1 gram water from 14.5 degrees Celsius to 15.5 degrees Celsius. Look here, the temperature is given specifically from 14.5 degrees Celsius to 15.5 degrees Celsius. Let me elaborate this. So when you take 1 gram of water and you increase the temperature of that 1 gram water from 14.5 degrees Celsius to 15.5 degrees Celsius, which is exactly 1 degree Celsius temperature of difference, the heat required is known as 1 calorie, right? So this is a precise definition of calorie. Now let us relate calorie with joule. Now the specific heat capacity of water is 4.816 joule per kilogram per Kelvin, or it can be written as 4.186 joule per gram per Kelvin. Now, what is the definition of specific heat capacity? Let me remind you, it is again the same one. Means it is the heat required to increase the temperature by 1 degree Celsius of 1 gram of water. So, as per that definition, it is here like if you want to increase 1 degree Celsius temperature of 1 gram of water, then you require 4.186 joule. Now, in the definition of calorie, we have seen the same thing, that the heat required to increase 1 degree Celsius of temperature of 1 gram water is known as 1 calorie, right? So it's very obvious that 1 calorie is 4.186 joule, right? 1 calorie is 4.186 joule. Now let us understand mechanical equivalent of heat. See, the amount of work needed to produce 1 calorie of heat is known as mechanical equivalent of heat. I repeat, the amount of work to be done for producing 1 calorie of heat is known as mechanical equivalent of heat. It's basically nothing but the conversion factor between two units, that is calorie and joule. It's a conversion factor between two units of energy, that is calorie and joule. This mechanical equivalent of heat is denoted by capital J. It is capital J. And this capital J is 4.186 joule per gram per Kelvin. Don't forget, this J is the unit joule and this J is known as mechanical equivalent of heat. Now let us move further. Relation between Cp and Cv. I hope you remember that Cp is molar specific heat at constant pressure and Cv is molar specific heat at constant volume. Now we know that molar specific heat capacity is given by C is equal to delta Q upon mu delta T, where delta Q is the heat required, mu is the mole number and delta T is the increase of temperature. Now when we talk about 1 mole particularly, then mu can be taken as 1 and so C will become delta Q upon delta T only. Remember this equation, C is equal to delta Q upon delta T. Now when we talk about constant pressure, so at constant pressure, from the first law of thermodynamics we remember that the heat required, that is delta Q, will be equal to delta U plus P delta V, where delta U is internal energy, P is pressure and delta V is change in volume. So the equation of Cp, that is molar specific heat capacity at constant pressure, can be now written as delta Q upon delta T at constant pressure. This P shows here constant pressure. But as we have written here that delta Q is delta U plus P delta V. So at the place of delta Q here, I will place delta U and P delta V. So I am getting the equation of Cp. Cp is equal to delta U upon delta T plus P delta V upon delta T. Let us name this equation as equation number 1. Now we also know that for 1 mole the ideal gas equation becomes PV is equal to RT, where mu becomes 1. And so you can also write P delta V is equal to R delta T. And from that we can write P delta V upon delta T is equal to R. Why I am making this equation? Because this is the same term in the right side of the first equation. So in the first equation at the right side I am going to put R at the place of P delta V upon delta T. And that's why the equation number 1 can be now written as Cp is equal to delta U upon delta T plus R. Here at the place of P delta V upon delta T we are placing R. So this becomes equation 2. Now at constant volume obviously we can write delta V is 0. There is no change in volume, that's why delta V is 0. And so the equation of heat from the first law of thermodynamics can be written as delta Q is equal to delta U plus P delta V, but delta V has become 0 and so this term becomes 0 and so you are getting delta Q is equal to just delta U. Delta Q is equal to delta U. Now we can write the equation of CV that is the molar specific heat capacity at constant volume, that can be written as delta Q upon delta T. Here is V. This V shows constant volume. But because delta Q is delta U now, so we can write CV is equal to delta U upon delta T. This is equation 3. Now from this equation, equation 2, and from this equation, equation 3, we can write that Cp is equal to Cv. See, this delta U upon delta T is nothing but Cv. So Cp is equal to Cv plus R, or you can write Cp minus Cv is equal to R. So this becomes the relation between Cp and Cv, that is a constant value and that is R. And don't forget, this is for ideal gases, because here we have used the equation of ideal gas, that's why this equation is applicable for ideal gases. Now let us see topic 12.7, that is thermodynamics state variables and state equation. Let us see. Equilibrium state of a thermodynamic system is described by a specific values of some macroscopic variables which are called as state variables. See, any thermodynamic system which is in equilibrium state, see, this is very important, that the thermodynamic system should be in equilibrium state. So any thermodynamic system which is in equilibrium state can have some specific values of macroscopic variables. These macroscopic variables are known as state variables. As we know already, like pressure P, volume V, temperature T, mole number mu, internal energy U, heat Q, these are all state variables. Okay. Now, an equation showing the relation between state variables is known as state equation. Any equation which is showing a relation between this type of state variables is known as state equation. For example, PV is equal to mu RT is a state equation for ideal gases. And here P, V, T, mu all are state variables. Now, every thermodynamic system is not always in equilibrium. It is not necessary that every thermodynamic system will be in equilibrium only. In that case, what will happen? In such situation, we cannot describe it by state variables or state equation. Remember this thing. If thermodynamic system is not in equilibrium, then we cannot describe it by state variables or state equation. Let me show you two examples here. Here the first figure A is showing one example and B is showing another example. Now in A, here is a container and here is one wall. In the left side of this wall there is gas, means the half of this container is filled with gas and the half of this container is empty. Now in this situation, when nothing is moving, in that case we can say this is a thermodynamic equilibrium state. and so we can apply thermodynamic state equation and state variable as well. But as soon as we remove this wall, the air from left side will rush to right side. So when the air is rushing from left to right, it's very obvious that in every part of this container, the pressure will not be same. You can understand here the pressure will be more, here the pressure will be less, and the same way density will be also different, and so the temperature will also be different, and that's why we can say this is not an equilibrium state. So we cannot apply the state equation, or we cannot describe it by state variables as well. See the second example. Here this example is of a fuel engine, right? This is a cylinder, here is a piston, and here is fuel in a vapor form mixed with air. Now when here an explosion takes place, the chemical reaction starts, and that's why everything is changing. The pressure, the temperature, the mole number, everything is changing. Even the piston is also moving due to the pressure, and that's why the volume will also be changing. So obviously this is not at all an equilibrium state, and that's why we cannot apply the state equation, or neither we can describe it by the state variables. Alright, now let us see types of state variables. There are two types of state variables. One is extensive variables and another is intensive variables. Let us understand this. See, extensive variables are such variables which depend on the size of the system. For example, mass. Mass depends on the size of the system, right? Then volume. More the size, more the volume, obviously, right? Then internal energy. See, more the size, more the number of molecules, and so more internal energy will be. Then heat. Though heat is not a state variable, but still heat depends on the size of the system. That's why it is extensive variable. Thus, these are the variables which depends on the size of the system, and that's why they are known as extensive variable. Now, intensive variable are such variable which are independent of the size of the system. Let us say density rho, pressure P, temperature T, etc. Let me explain you this with some example. You take a container filled with gas, alright? The pressure is P, the volume is V, the temperature is T, and the density is rho, alright? Now you divide this container into two parts by putting one wall in between, alright? So when you put a wall in between, it is converted into two containers of half size. So here the volume is half, but the pressure will remain same in both the containers. The temperature will also remain same in both the containers. The density will also remain the same in both the containers. So the size is half, still the density, the pressure, the temperature doesn't change, and that's why it is not size dependent. So it is known as intensive variables. Alright, now when you multiply any extensive variable with intensive variable, it becomes an extensive variable. If you multiply intensive with intensive, then obviously it gives you intensive variable. If you add extensive with extensive, it gives you extensive. If you add intensive with intensive, it gives you intensive. But if you add intensive with extensive or extensive with intensive, whatever, it is not possible at all. It is not possible. It is something like adding two different physical quantities. If you remember, in dimensional analysis, we have studied that we can add two physical quantity of same dimensional formula or same units as well. But we cannot add two physical quantity of different dimensional formula or different units. It is the similar here. We cannot add intensive variable and extensive variable with each other. Though we can multiply extensive and intensive variables and it gives you extensive variable, but we cannot add extensive and intensive variable. That's not possible. Alright. Now let us see this example. We know this equation delta Q is equal to delta U plus P delta V. Now the first one, that is delta Q, is obviously an extensive variable. Delta U is extensive variable. P, pressure, is an intensive variable, and delta V, that is volume, is again extensive variable. But here P and delta V are multiplied, so intensive into extensive will give us again extensive. So you can see that here extensive is equal to extensive plus extensive, right? That means on the left side and the right side of this equation there are similar type of variables, that is extensive variables, and so this equation is correct. This is a very good practice to check the consistency of thermodynamic equations. By this method, you can check the thermodynamic consistency of any thermodynamic equation. Obviously, if you are getting both the sides like intensive, then the equation is correct. If you are getting both the sides like extensive, then also the equation is correct. But if you are getting intensive in one side and extensive on another side, or vice versa, then that equation is not correct thermodynamically. Alright. So this is a method by which we can check the consistency of any thermodynamic equation. So herewith guys, I complete my lecture today here, and let me tell you, the whole writing work whatever I have done today in this lecture has been saved in form of PDF, and the link of that PDF is given in the description. You can download and can write down the whole lecture the way you want. I also recommend that you please note down all the equations that are given in red brackets, because these are very important equations and that will be very much useful for solving numericals and MCQ as well. Alright. So herewith signing off, Anshuman Baldania.